Okay, we'll get started. Welcome to the IRSIG webinar series. Today we are very fortunate to have Dr. Phil Korngut from Caltech come and talk to us. Many of you on the line I know Phil already, so I'll refer to him by his first name. Phil received his PhD in physics from the University of Pennsylvania in 2005, working on Mustang, which was a SZ camera for the 100-meter Green Bag telescope. Following that, came to Caltech and JPL, where he had a NASA postdoctoral fellowship working on CIBER, which is what he's going to talk about today, and then later CIBER 2. And after that, subsequently went on to become the instrument scientist for NASA's SPHEREX mission, which is taking up a lot of his time these days. And we have some interesting results here, so I will shut up and let Phil tell you all about it.
All right. Well, thanks a lot, Mike, and thanks a lot for having me here. Very excited to start to share some of the work that we've been doing with the CIBER narrowband spectrometer. So my slides look okay. Are we good to go?
Looks good.
All right. Well, thanks again. My name is Phil Korngut from Caltech, and as Mike mentioned, I've been working on CIBER and now the CIBER 2 sounding rocket programs for a long time, and currently spending most of my time working on the formulation of the SPHEREX mission for NASA, which is also spanning the near infrared. So to get in, let's see if I can. All right, here we go. So ubiquitous picture of the look back time on the history of the universe as we now expand it. So of course, in this cartoon, we are looking in time from left to right, and to first order, the size of the circle at that epoch is going to represent the scale factor in the universe. Now, in cosmology, we're all very familiar with the wonderful tracer that is the cosmic microwave background, which is, the signal, a beautiful black body that is the remnant of the Big Bang after the universe cooled enough to become neutral and emits a black body. But when we look back and study the cosmic microwave background, we're really looking at this kind of shell, right? It's very two-dimensional because it corresponds to the surface of last scattering when, the universe cooled enough to become neutral. If we make a similar measurement in the near infrared wavelength range, which is where we refer to that background integral as the extragalactic background light, it's no longer such a thin shell, right? We're looking at the integral of the emission of light production through cosmic history, and depending on how far back and what redshift we're looking at different sources. So, at high redshift around Z of 10 or, going up to 12 or whenever, the first stars are lighting up and really bright in UV and Lyman alpha and reionizing the universe, those sources, if you think about 12, 16 angstroms at Z of 10 or so, that's gonna fall in the near infrared band. And then, as you move along in the evolution of the universe, stars aging, and even in the local universe, older red stars are going to intrinsically peak in the rest frame in the near infrared. And of course, we've got the signal that comes from the galaxies themselves and those sources, and perhaps even more exotic things like primordial black holes at high redshift. But then as the universe evolves and galaxies merge and stars get tidally stripped and thrown out to the high radii of those universes to make a diffuse glow like the intrahalo light. So that's in the near infrared. So when we talk about the extragalactic background light in the near infrared, we're talking about that integral, and all of those sources are in there. But what is their total production? And what is what are their spectral characteristics? These are the things that we're trying to understand as this kind of cornerstone of observational cosmology. If we take a look, this is a summary of what the absolute spectrophotometry in the field kind of looks like. This is from about 5 years ago. I'll show more versions of this plot. And people who work in the field know that there are many versions. So if your data point's not on here, it's not because of an exclusion. It's just it's a big story to tell, and we're going to focus in on a few. I'm also going to just shade out the kind of far infrared portion of this, and we're just gonna focus on the near infrared. Now, take this plot as in context with its analog, for instance, like the FIRES black body spectrum and all of the wavelengths that have been put on top for the cosmic microwave background, which is just, in perfect agreement with really small error bars that spans. In the near infrared, it's a much more complicated story, kind of observationally. And I'll take you through this plot a little bit because there are many different types of measurements being shown on here, and I'm going to highlight a few. First, what's shown here as lower limits, if we look at what we call the integrated light for galaxies. So you can there have been many studies where you do deep source counts you take a big telescope and you integrate really deep onto cosmological fields, and you do photometry on all those individually detected sources, add up all those photons. This is a minimum of what the total light can be, right? So the IGL is at least a lower bound on how bright the glow of the integrated background can be. And you can see the galaxy counts have a nice peak around a micron and a half, and fall off, and then it's nice and contiguous from some of these HST and deep ground-based measurements going out towards IREC. And I should say this is taken from a summary paper from Asantha Kure, and you can see the references therein that lots of work went into all of these data points. And so that forms our lower limit. The blue shaded region is a completely different measurement technique. And this is an interesting way to constrain the absolute spectrophotometry, which is done indirectly, because in the gamma ray world, they look at blazars with kind of known power law spectra. And of course, those blazars, which are at cosmological distances, will have to go, all the photons that come through there will have to traverse the, intergalactic, light field, and there will be a Compton scattering due to the interactions between those gamma rays and the intergalactic light field. And so they've got these constraints and the actual detections. This is from the HESS collaboration. There might be some newer ones as well, but this kind of gives our another measurement, and this is kind of an indirect measurement of the total light field. And you can see there's some evidence that it could be in a little bit above where the galactic source counts add up, which could leave open for some additional signal. And then you've got a third class of measurements, which are shown at top, and those are the absolute photometry measurements. So those many go back to Derby, and as well as what's IRTS was a Japanese satellite. And so those measurements are seeking to really just add up all the photons and account for all photons that you measure in an absolute way, and to tease out which is coming from outside of our galaxy and put that on here. So you can see there's still kind of a pretty large range between what we expect from the galaxy counts and what the absolute spectrophotometry measures. Even within absolute spectrophotometry, there's a range of reported measurements, and this can span an order of magnitude. Obviously, if that's a real discrepancy between galaxy counts and absolute spectrophotometry, there's lots more photons coming from somewhere that we have to disentangle. And if it's not real, then there's some systematic that we have to understand, and everything needs to be reconciled before we have a nice, clean picture of what's making up the background light. This is made so difficult in part by the zodiacal light foreground. So we live in most of our measurements, the most convenient place practically to make measurements is at 1 AU from our humble home on the Earth. which unfortunately is embedded in this interplanetary dust cloud. So we're living in our foreground. You can see this is just a picture taken from Earth where the galactic plane is up there and this kind of false dawn, which is often referred to, which is the zodiacal dust from the interplanetary dust cloud. Just to give you a sense of kind of the the magnitude of this effect, if we just take the brightest reported EBLs, which go up around 70 nanowatts per meter squared per steradian at 1.4, this is kind of like at the early IRTS levels, and then just compared that to what the zodiacal light is at, say, the north ecliptic pole, or even at 10 degrees ecliptic latitude. These are, of course, approximate spectra, but you're really looking at kind of, at best case, kind of a 10% effect. So if we're trying to measure precisely the absolute contribution from the EBL, it's really hard in front of this huge foreground, which you can't get away from. At least at 1 AU, you can't get away from it, no matter which direction, even if you're pointing at the pole, because we live inside the cloud. You can't get away from it. It's further complicated because that foreground, of course, is really local and varies with time. So this is due, you can think about the geometry if we're on the Earth going around, and the interplanetary dust cloud is inclined on its orbit. So whenever we're making a measurement, say, as the arrow shows, if we're making a measurement up towards the north ecliptic pole, in the summer and in the winter, we're looking through totally different dust columns. So we're looking, the amplitude of the foreground is going to vary as a function of time, and of course towards what direction you're looking at. So these images, which are in a movie, correspond to the weekly maps from the Derby mission. This is at 25 microns, which is near where the emission of the Zodi peaks. And you can see as, so the kind of donut shape, that has to do with the Derby scan strategy, which was kind of carving out these great circles. And as, the orbit precesses around the Earth, you're looking at different chunks of sky. So it's a great circle that's precessing around, but you can see in the color scale, these are in galactic coordinates. So you can see the emission from the galactic plane there, but the ecliptic plane, which forms this kind of zigzag across, you can see the really bright emission from the Zodi, and of course you can see that it's varying with time. So this is a difficult problem, and in order to get to those absolute spectrophotometry measurements, we've got to tease out and quantify really precisely how much of this light is coming from the Zodi and subtract it. The Kelsall et al. Team from Derby in 1998 did a really amazing job modeling this this annual modulation to fit a geometrical model, parameterized with, I think, 20 some odd parameters to fit what was being observed in this modulation. So you can see at different wavelengths and at different positions, you can see as a function of time, this is how they fit the annual modulation and generated this geometrical model, which includes a dust cloud, and then there's some other stuff like these bands and a ring. There was also a component called the Earth trailing blob. And so this model was actually pretty remarkably successful. It does a really great job of predicting this modulation. Of course, it is, it's a geometrical model of a really complicated system, and it has its limitations as well. There was another attempt at modeling this foreground with also on Derby data from Ned Wright around 2001. And this model kind of took a little more aggressive approach. And they said, let's make the assumption that at 25 microns, the entire sky is dominated by Zodi. And then if we know the spectrum of the Zodi, extrapolate down to the near IR to estimate how bright that is there. So these two models have really been very important for spectrophotometry studies for the EBL, and they kind of bookend where those go. If we look now, this is another plot. This is a different paper, but the same spectro of the EBL, absolute intensity. This comes from actually a paper from Matsura et al. In 2017, which was based on another instrument aboard CIBER. And what you can see here is in the color scale, the EBL reported in this paper was actually reported, we reported it in 3 different assumptions. So in the red is what happens when you get this near infrared spectroscopy, assuming a nominal Kelsol model. So this is just taking the model predictions and subtracting out a spectrum of the Zodi normalized to Kelsol. And you get quite a large excess over what this black line is showing, the IGL, approximate IGL. So, if we take that, there's an excess detected. If we look at, the right model and subtract the same data, you get a much lower, even possibly going through 0 towards the bluer end of the measurements. And then there was also reported a kind of a, just based on the color, what we call a minimum EBL. If you assume that the EBL equals the IGL in the kind of 800 nanometer region, what is the spectrum of the residual? So that's this blue one. So the point being is that our qualitative understanding of how bright this EBL is really tied to how well we can understand how much contribution we're getting from the Zodi. So if there's another technique that can begin to suss out, kind of where we are in this parameter space, it's really valuable. Another possible technique is using Fraunhofer lines. So Joseph von Fraunhofer, who was active kind of the early 1800s, was, once spectroscopy came around, realized that if he dispersed sunlight, you have all sorts of absorption lines. We now call those, he bears that name, we call these the Fraunhofer absorption lines. And in particular, relevant for us, is a really deep calcium triplet at 8542 angstroms. And this is interesting because in that region, kind of short of 2 microns, the dust cloud, this zodiacal light, is really just reflected light, sunlight. So you've got the sun lighting up this dust cloud and it'll reflect back. So we're measuring basically the spectrum of the sunlight. Now, the sun is one thing that we have really well characterized spectra for. And these calcium 2 lines are of quite well understood depth. That means if we measure how deep the line is, that gives us an idea of how bright the intensity is. So if you have an extragalactic background, which is smeared out in redshift and spectrally featureless across this region, adding on top of it will just shift this spectrum up. And so still we can measure the depth of the line and not worry about the DC offset, just use the ratio of the depth of the line to infer how bright the zodiacal foreground is. So this is a different independent technique that we're seeking to employ here. Another quick point that should be made is just that from ground-based astronomy, it's really difficult to do absolute spectrophotomic measurements in this wavelength region because of the air glow. So OH molecules in the upper atmosphere are glowing. This is, orders of magnitude brighter than the Zodi itself. So that makes it really hard. They're also not stable. This is some measurements from Kit Peak in H band of what that might look like over 45 minutes. And so not only is it glowing really bright, but it's also changing with, the dynamics of the upper atmosphere. So it's difficult to do this from the ground. This is why it was a nice niche for a sounding rocket experiment. So CIBER, which stands for the Cosmic Infrared Background Experiment, was a NASA sounding rocket mission that we deployed sort of in the range from 2007 to 2015. And CIBER was really targeted as a multi-pronged approach to tackle this infrared background problem. We had this, what we call the low resolution spectrometer, the LRS, which was an R of 20 spectrometer from 800 nanometers to 2000. That was the results that I just showed from Matsura et al. 2017, but there was also a few more from, on the spectra of the Zodi and the DGL, which I'll loop back around to. There's the narrowband spectrometer, which is what I'm going to talk to you about in this work. And also we had dual band wide field imagers at 1.1 and 1.6 microns. These were targeted at measuring the spatial fluctuations in the IR background. And there is a number of papers, which I'll point you to. Mike Zemkov's paper in 2014 in Science, which quantified the fluctuations in the IR background and found some hints that there might be quite a bit more signal in the IHL than we had thought. And recently, I'll just also point you to Yunting Chang's paper, which was a stacking analysis based on these, which has some interesting direct constraints to the extended profiles of galaxies. The NBS, or narrowband spectrometer, is targeted towards this Fraunhofer line study. And the way we did that is to have a really fast optic. So this was f0.9 optics to make a huge field of view, refractive optics that included this tipped interference filter targeted with the narrowband. So the way that works is that with this huge field of view, so it's an 8-degree field of view imaged onto a Teledyne Picnic, which is 256 pixels wide. And the central wavelength is a function of position on the field of view. So this is a map of the wavelength as as it lands on the pixels. And this is specifically targeted towards that calcium absorption line at 8542 angstroms. If we look at what that would look like, so this is actual measurements we made of the solar spectrum. So coupling via fiber into the laboratory into an integrating sphere and measuring the spectrum of the sun and comparing that to some archival, really high resolution spectral data from Dilbouil et al., which is the red line, convolved with all of the instrument parameters which we measure. So this includes flat field, the spectral response function, and wavelength calibration map. So this is an ideal measurement of what that calcium absorption feature will look like on our narrowband spectrometer. And it should be noted that in this fit of the red to the black, there's only one free parameter, which is the relative amplitude. In this case, that bears no interest. That just has to do with the efficiency that we're coupling the sunlight via fiber to our sphere. But without an offset, you can see that it's a really nice constrained relationship between the depth of the line and the absolute continuum amplitude. And that's what we want to exploit to try and measure what the absolute Zodi is, so that we could, potentially provide foreground removal for EBL studies. Those 4 instruments were co-mounted onto a liquid nitrogen cryostat, and we had a series of deployable cryogenic baffles to block out large angle thermal emission from the rocket, as well as off-axis emission. So you can see there these 4 deployable baffles. We flew CIBER a total of 4 times. The first time was an engineering flight from White Sands, and then flown twice more on a Black Brant 9. That's a 2-stage sounding rocket from White Sands Missile Range in New Mexico. And the 4th time in 2013 from a Black Brant 12. This gave us an extra couple hundred seconds of data, but was unrecovered and went intentionally went into the Atlantic Ocean. It wouldn't be a cyber talk if I didn't show a video of the rocket launch, and it really is a super fun way to do science. Ground-based astronomy doesn't get the heart pounding. I'm not sure. I don't think Zoom is going to stream the audio, which does improve how dramatic this video looks. But it really does give you a sense of how exciting this kind of science is. Our sounding rocket flight is kind of outlined here. The first stage only burns for 6 seconds, at which point you're going at Mach 1.7. So the acceleration is truly remarkable. It's not like when you picture, the space shuttle taking off, and it just kind of hovers over the launch pad before it accelerates. This goes right to Mach 1.7 after a 6-second burn. The second stage, the Black Brant, ignites at 12 seconds, and then by the time that's done, you're going at Mach 6.6, after which it's just a ballistic flight. So we launch really high inclination. Once we get stable and flip around and de-spin, we have this door which seals our cryostat on the ground, and then open that up, which will deploy our baffles. So these cryogenic baffles come up, we take our measurements, and then the door closes. And after our measurements, which is our observing time, is on the order of 400 seconds, and we reach an apogee of around 330 kilometers. This is from the 2 stage, after which point parachute deploys, and we go get it in the desert. Here was our landing in 2012. As it lands out there in the middle of the desert, you can see the parachute. This was kind of a pretty textbook landing. You can see we landed in a nice, soft, sandy area, and the U.S. Army and the Air Force come and get us in a helicopter, and we bring back the payload, which is it's just quite, it's a really fun way to do science. In terms of hours of work for seconds of data, it doesn't look great in that Venn diagram, but it is a really fun way to get science, as well as, the infrared background is one of these things where you can actually make meaningful measurements in those short sounding rocket flights, as long as we're above the air glow from the ground. The fields that we study are varied in their ecliptic and galactic latitudes. So we go from the north ecliptic pole and then have a few low ecliptic latitude fields. But we're really, as I'll get into in a minute, trying to tease out select fields that have different contributions from things that correlate with ecliptic, the Zodi, and galactic, which is like the stars and the DGL, which I'll get into in a minute. So this is what a raw output of the NBS looks like. And we're trying to extract the calcium absorption feature, which looks like that. We take it through generally the standard processing. So first we got to subtract off a dark current and mask out all the nasty pixels, which gets us to something that looks like that. I'm going to just convolve just for ease of illustration. We don't do that in the analysis, but you can see now the NBS is actually, it's an imager. It's just that the wavelength of each pixel varies slightly depending on where it lands within the field of view. So you can start to see now this broad feature of a uniformly illuminating Zodi, but also you have all the stars and galaxies which land on the pixel. So we have to do something to get rid of all those point sources. We build up a template image of what those stars look like from an ancillary catalog and generate a mask. I'll talk more about the details of that in a moment. And then now we can start to, if I just bin by wavelength, you can see that signal to noise is really not an issue. We have a whopping detection of that calcium absorption feature in the Zodi. Now the task is to tease out and quantify how much Zodi is in there. And so to do that, we have to separate out all of these components. So here's kind of our top level equation. I've written it out into a series of 5 terms. This is what we measure, which is the sum of all of these things. And what we really want is the amplitude of the Zodi. So in this, all of the components are listed as separate terms. The A's are the amplitude factors. And here's the terms that we're interested in. Of course, there's Zodi. There is the diffuse galactic light, which is scattering off. It's a similar mechanism to what we're measuring to Zodi, but now we're talking about the interstellar radiation field and how that scatters on the ISM. We have starlight, which I break into 2 different terms, which I call bright ISL and faint ISL. Of course, bright and faint are subjective things, but really the difference here is the bright is the stars which we detect enough that we can mask individual stars based on their location, but we only have so many pixels and the pixels are large. So we can mask all the way down. And in fact, we can really mask pretty shallow but before we start running out of pixels. So then there's the next term of the faint interstellar light. which means we have to rely on the ancillary models of the galactic star population to model the integrated flux. The F's in this is the spectral response of each individual component. So really that means how deep the calcium absorption profile is for that component. And the G's are the spatial distribution of those. So note, I'm not including a G for the faint ISL. We assume that to be uniform for our individual targeted regions in the galactic plane. And then we have to rely on ancillary measurements that give us these sorts of spatial variations of each individual component. And we've got an amplitude parameter for each of those components. And then, of course, each is a bandwidth integral when measured through the bandpass of each pixel of the narrowband spectrometer. So to start on the bright star removal, this is what a star field would look like for the NBS. I'm zooming in onto a little chunk. And if we zoom in even further to a few stars, remember this is 2 arc-minute pixels, so this is really quite a large field of view, and we're looking at the brighter stars. We rely on an ancillary star catalog. In this case, we employed the U.S. Navy's DSS survey in the I2 band, which is an 880 nanometer, so it's really close. It's the closest all-sky star catalog we could find to the NBS wavelength. And it covers obviously all of our fields. So we take this catalog and generate a template image based on a stacking analysis, which we use to reconstruct our PSF. So this is what a PSF looks like after stacking. We are stacking in a subpixel. So you chop each pixel up into 10 or so, 10 by 10 or so subpixels, and we can reconstruct a little bit more what that intrinsic PSF looks like. Use the catalog and the fluxes and positions to regrid after we've solved for the astrometry. And you can see on my zoom in, if I click further, there's green contours. Those green contours come from our template image from the astrometry and the PSF and the flux in the catalog. So we use that ancillary to generate a mask. And we've got a few parameters which we can use of how aggressively to mask as a function of, radius for a source and, what our cutoff magnitude is. And of course, the task here is to understand what's below. So now we add this faint ISL component, and that's generated from what we use as the trilegal method. So this is a publicly available code from Leo Girardi, and they've taken these band passes. They have models of the galactic plane, the galaxy and the bulge and the disk, and you give your coordinates and which wavelengths you're interested in. And they'll give you a statistical representation of what the star field is made up of in that region. So I'm showing here a test, which is a differential test. Of course, we have no test which can get us at what's the residual star count below, but I can do this differential test. So what you're seeing is in this animation, for each frame, we're turning the knob on our masking threshold parameters. So that's kind of the radius and the depth at which we're masking. And this really just goes down to like sort of magnitude 12 AB is kind of the deepest we can go to, but below then we start to lose a lot of pixels. So for those 2 parameters, we're turning that knob, and I do so on my real data, which is masked on the real DSS catalog, and we see what happens to the amplitude in the background. Do the same thing on our totally simulated image, which takes our wavelength distribution of the NBS and the simulated source counts for both the bandpass at 880 for DSS and at 850 for the NBS. And so if everything is right, where our model is a good description of our data, we should get when we make our differential, you should get a slope of 1, which is that red line. So this is shown for a single field. When we do this test for all fields, you can see this is our 9 fields that were observed, and the black line is unity. And for all of these things, we have an average correlation of 1.0 plus or minus 0.1. So that's actually quite reassuring. That means that at least gives us an upper bound on the confidence between our calibration, our astrometry, our PSF understanding, and perhaps more importantly, that we assume our assumptions of the absorption depth in the integrated stellar light field is near solar. And that assumption is actually backed on, I didn't include a slide in it here, but from studies that were made of the stellar populations and measurements by Matilla et al. As a function of galactic latitude, and found that the equivalent width of that CA2 line is near solar, within a few percent. And you can see at least at the 10% level, which includes all of these effects, we're holding together. But of course, to estimate the contribution from the residual stars, we have to rely on the trilegal model. The diffuse galactic light is also going to contain some absorption, because this is the starlight that is scattered off the interplanetary dust. To estimate that, we're relying on these scaling relations. So this is from Arai et al., which actually also came from the CIBER LRS. And in which case the x-axis here is the near infrared wavelength, and the y-axis is the intensity at 100 microns. So this takes a template of the star, the SFD maps, Schlegel, Finkbeiner, and Douglas, for the 100 micron IRAS data, which is going to trace the interstellar medium, the dust in interstellar space. And this gives us a template, if we take that map, how to scale it for a given wavelength to what we might see in the near infrared. So this is what that map looks like for our 9 fields. And of course, now we get into an interesting interaction because of the way that the NBS works. So because the NBS is really designed to measure a uniform illuminating field with its tipped filter interference design, any spatial structure that just randomly lies across the field of view needs to be understood, because it will interact with that spatial spectral coupling. So this is what it looks like if we don't include the calcium absorption of the dust. If I just flip, I can go back and forth, because that dust will have the CA2 line as well. And I just want to show how important quantifying this is in 2D map space, because that random orientation of the dust clouds on the NBS field of view will form errors in your 1D spectrum, which you eventually extract. So in this case, I'm just taking a single field and just randomly spinning around the orientation of what that dust would look like on your field of view. And you can see the black line is the intrinsic Zodi that we're trying to extract. This is a perfect uniform Zodi illumination with the calcium absorption line. And then we'll take the same DGL and just spin it around. This is the sum of those two at the north ecliptic pole, which actually has a lot of these dusts. And you can see the red line is changing a lot. So it's very important to model all of this in full 2-dimension with your astrometry registered, and the interaction between the spatial distribution of the dust and the spectral calibration of the NBS. The same thing is true for the gradient in the Zodi. And this was a complication that we're actually going to have to rely on the models for, because at 8 degrees of an instantaneous field of view, the tip across the field of view to the plane is actually too much that you can't ignore it. So again, this random orientation of how our filter aligns with the ecliptic plane is going to affect the inferred amplitude. So we rely on the CalSol model just in terms of how much across our field of view that is going to model vary. So you can see now this is what the actual templates we're fitting to, which include that spatial gradient and that uniform CA2 absorption feature across your field of view. So this has to be taken into account, and also gets to go in the systematic error budget, which I'll get to the breakdown shortly. So after accounting for all of those components, we add in, based on ancillary data, our estimates for what the DGL, the ISL, and the Zodigrad look like. So we'll make a template 2D image of what those fixed components are and float only 2 components to fit. So we're floating an amplitude of the Zodi, so which will make that line deeper. And then we, of course, leave a featureless offset, which includes, EBL and all the other stuff like residual air glow or residual dark current and those sorts of things, which will provide a featureless offset. So you can see it's quite interesting. The shape of the red profiles is different in each field. And the black data points, which is what we measure, and this is only statistical error bars shown here, trace those odd shapes quite well, which means that we're doing something right in terms of those gradients and the spectral alignment of the random DGL. So from these fits, we do, we get an error bar, which just comes from the delta chi squared from these statistical error bars, as well as marginalizing over that offset parameter. And this is what the statistical only distribution functions look like. And from this, we're kind of getting to the scale of, sort of 1 sigma equals 20 nanowatts per meter squared per steradian as an uncertainty on our Zodi foreground, which is reasonably interesting if you can, root n that and get down to kind of the single digit nanowatts for an uncertainty. But of course, this is not including all of the uncertainties in all of those models. And we have to propagate that all the way through before we can begin to test the models of Kelsall and Wright, and with the goal of getting towards how much Zodi do we remove to get an absolute EBL. So this is a compilation of all the different parameters that are included in that fit and the allowed uncertainty that we move. Your EBL should not depend on your choice of masking. Masking is some arbitrary, choice. The universe doesn't care how big my pixels are. So your estimate of the absolute Zodi needs to be independent of your choice of masking threshold. The DGL scaling relation, as well as the trilegal model, which we're relying on for subtraction of the ISL, have their own uncertainties, which is on the order of plus or minus 30%. We also have our absolute calibration. Now, I didn't really go into how we absolutely calibrate the NBS, but it's an extensive campaign that goes back with in concert with NIST, in which we use their Circus laser facility and scan across the wavelength range with absolutely calibrated radiometers. We've measured this parameter before and after sounding rocket flights, and the variation in all of the measurements, which was about 4 or 5, is on the order of 2.5%. So there's an absolute calibration error, which moves everything up and down that we have to deal with. There's also, because we're now comparing to the Kelsall and Wright models, which are at 1.25 microns based on Derby, we have to correct for the spectral calibration, the intrinsic spectrum of the zodiacal light. And that goes from, it's around a 1.25 factor correction, but we have a few percent error on that as well. And this comes from the template that we measure from the LRS in the same fields. So any spectral variation across the Zodi should be included in that. And we've got to take into account this multiplicative factor. And of course, we've got flat field, but that's quite far subdominant in this case. It's useful to illustrate how different fields are subject to different amplitudes of systematic errors here. This is just for illustration. I define this parameter AZL, and that's basically calculated if I take all of those systematic errors, put all of them to their nominal values, and vary one to the max and min of the range of allowed uncertainty, and then show that as a fraction of the recovered nominal Zodi of how much it varies based on that. So in this case, one axis is the fields we're looking at. The other is the individual systematic. Q is just all the multiplicative systematics, including calibration and flat field and the spectral correction factor. And AZL, of course, is this how much the parameter moves. So you can see, for instance, for the low ecliptic latitude fields like ELAT 10, we're dominated by this multiplicative effect. At the north ecliptic pole, where the Zodi is really faint, but it's kind of reasonably low galactic, we're completely dominated by the ISL. And if we look at the DGL in these different ranges of ecliptic latitude, the contribution varies by over an order of magnitude. So you really have to explore completely this parameter space for each field, for each allowable systematic error range. This is what the systematic distributions look like. So after we explore fully, it's not a Monte Carlo because I'm not trying to solve on individual parameters. I'm just exploring the entire parameter space allowed by those systematics I just enumerated, and you see how it moves around. So you could see there's another 30 or 40 nanowatts per meter squared per steradian that's included from this kind of systematic. So now we combine our statistical and our systematic errors, and we can at a position where we can compare to the models and see how well we're doing on absolute comparison. So what you see here on the left, on the x-axis is the Kelsall model. On the right x-axis is the right model. These are the predictions for our fields at our epochs of observation, the intensity at 1.25 microns Derby band. And on the y-axis is the NBS inferred Zodi only component scaled to 1.25 microns. So you can see the correlation is good, of course, in both cases. The color scale on the background shows a 2D representation of those 1D systematic error probability distributions that I just showed. The blue error bars, you can see there are 2 error bars. Those correspond to 1 sigma just from the statistical fits of those 1D spectra, and also combined with the sigma that comes from the statistical only, which is that color scale in the background. So we're looking really at the blue, the outermost blue points, and comparing that to the model. The solid green line in both cases is unity. Is y equals x. And the dash line, which is somewhat interesting, is if we allow for a single free parameter, which is an extra offset that would be sort of a component of the Zodi that doesn't vary with season to season as we go revolve around the sun through the IPD. If we take that in terms of chi-squared to say how well are we doing in a model test of each of these, if we just leave it from the green line, a reduced chi-squared for the Kelsall model is not very good. You have this broad distribution, and again, this is calculating the reduced chi-squared for every iteration of our systematic errors. So we explore that parameter space, and within that parameter space, we calculate chi-squared to the Kelsall model and the right model every time. If you just take it at face value, the reduced chi-squared from right has a mean value of 2, which is interesting. And you could see that because in terms of an overall DC offset, the right model is spanning our measurements pretty reasonably. The best chi-squared comes from this minor modification. So of course, chi-squared gets an additional degree of freedom, but even with that additional degree of freedom, both cases improve slightly. But the Kelsall model with this offset allowed, which is a very simple modification, the simplest thing that we can do given the size of our error bars to see if there's a better description. And in this case, we get a really nice centrally peaked chi-squared distribution with a mean value around 1.5. So we're getting into the region, which is actually a pretty good description of our data set. So if we turn that around and say, if there's some kind of isotropic or at least non-varying with annual modulation amplitude parameter, what is its value and what is its uncertainty from this? And so basically, this is again exploring the full range of systematics and calculating chi-squared, and a best fit offset to each iteration. The right model is basically within 1 sigma of 0 in terms of an offset. So this is not any significant deviation at all for an extra source of Zodi. From the Kelsol model, we are about 2.5 sigma away from 0. So, this largely comes from those multiplicative systematics. They'll move everything up and down together, right? So it's not an obvious slam dunk. We're at the 2.5 sigma, which can be kind of a psychology experiment for many scientists, but it's an interesting amplitude. So it's kind of 46, but the uncertainty on it is on the order of 20 nanowatts. So it's an interesting thing to speculate on. If we compare to some other studies that are in the literature recently, it might fit in quite well with some inferences that have been made, and kind of I think it's an interesting culture thing between the people that are interested in studying the Zodi as as an IPD, as a science topic, and the people in cosmology who are interested in studying it as a foreground. The dynamical simulations, so this is from Poppy et al. 2019, include this large isotropic I shouldn't say isotropic, I should say spheroidal component, which they call OCC, and attribute to a debris field from the Oort cloud comets. Another study, which was recent from last year, Sano et al., which they did a reanalysis on Derby, but subdivided these fits in bisolar elongation. So trying to use that dependence of solar elongation to tease out. And they found the data better fit by including a component which looks a lot like the OCC. So this is like a spheroidal component. And that amplitude is pretty large, and one of their model fits at the order of 20 nanowatts. So that's, within basically 1 sigma of what we're seeing as that offset. Even further back, there was a paper, Nesvorne et al. In 2010, which included this kind of component to fit to 25 micron IRAS. So it is not unreasonable to think there could be some cometary origin debris field. The Kelsol model did a remarkable job of fitting this geometrical parameter, but it's just by construction insensitive to something that is big and smooth, right? Because it's using the annual modulation. The right model, on the other hand, takes the integrated flux and then scales that down. So it would be sensitive to this sort of thing, which might explain again, why the DC level on the right model is more in line with what we're seeing in the NBS. But the Kelsol model does a better job at describing our field-to-field scatter. I'll also point out this was another EBL study, of course, recently from Lauer et al. It's got some press from the New Horizons, where they actually left our foreground, right? They went all the way out to 40 AU, tagging along on that trip to Pluto, and repurposing that New Horizons to do the EBL. And they included, nobody's in this paper, nobody was really quite concerned of what was going on at the left hand of this plot, which is just the brightness as a function of heliocentric distance. They were working out here where the foreground is kind of 1/10 of a nanowatt or so. So it's really negligible. But they include this blue curve, the OCC, at the kind of 10% level at 1 AU. So these dynamical modelers have been including this component for a while, and it is a feasible interpretation that what we're seeing here as this offset could be attributed to this kind of component. So in conclusion, I hope I've summarized well our study for using these Fraunhofer lines as a way to get at an independent kind of test of the models for the zodiacal light. We have some evidence at modest significance of an extra component in that would vary very slowly with annual modulation. That kind of hangs together with the OCC component that's been popular in the dynamical modeling of the IPD recently. And I think this method is promising. If there are future opportunities for small satellites, you don't need a big telescope to make these NBS measurements. The NBS was largely geared towards small, because we had that short amount of time to make those measurements. So we had to make really big pixels to get our throughput. If you have more time and space, you can make smaller pixels, mask deeper, and have smaller variation across your field of view. You could really start to test this well, and hopefully can start to converge on an absolute EBL measurement that's gotten past the foreground removal systematics. The uncertainty in this measurement was a little bit large to really get compelling constraints, but we can infer from the measurements of the absolute spectrophotometry, which rely on either the Kelso or the Wright models. This would imply that, Kelso alone models are missing some of that foreground flux. Can't be all of it because, for instance, on the LRS measurements, that spectrum is red, and we know that the Zodi is blue. So some component could be from Zodi, but not all of it. So I'd like to thank you again for having me here. And I'll just also note that a couple of weeks ago, we had our first flight of CIBER 2, which went quite well. This is the next generation IR background sounding rocket experiment. Doesn't have an NBS on it, but it does contain both 6 bands of imaging and a linear variable filter, which will be used for this absolute spectrophotometry as well. So thanks again for your attention, and I hope you enjoyed it.
Thanks, Phil, for the excellent talk. Let's give Phil a virtual round of applause. Okay, we don't have any questions in the chat, so we do have a couple minutes for questions. So if anybody has anything they'd like to ask, feel free to unmute and ask away.
Okay, Phil, this is Roger Winters. I'll speak up. Very nice talk. Could you think of a way to maybe extend this work with JWST, with the appropriate spectrograph, further into the infrared? Of course, JWST will have its own issues with stray light, but could that be useful?
I think I did think about that briefly. Of course, JWST will have awesome, spectral capabilities. I do think you hit on the thing that's going to make that hard, is that, you have spiders and you have segmented mirrors and there's no baffle. So your stray light, you'd have to get a good model of that. But we're talking about big diffuse sources. And of course, with JWST, you could get not just one Fraunhofer line. You could probably get the magnesium ones and others. So that's an interesting point. Of course, also JWST is at L2. So you'd have to do a little bit more work on that geometry. You can't just use the canned foreground code. You'd have to, there's different lines of sight and for where it is at which point and what column you're looking through. But that is an interesting idea. And I think someone should probably, the spectra of diffuse sky are going to be glowing with those Fraunhofer lines. So it's an interesting idea.
Okay, thanks.
Time for another question.
Hi, this is Rick Arendt.
Hi, Rick.
When you were comparing the results with the Kelso and Wright models, were you using data from all 3 flights?
Yes, so that's a good point that I didn't, let me go back to that figure. Sorry. That's a good point. Thanks for bringing that up. So you'll see there are 3 different symbol marks here. There's triangles, circles, and X's. Okay. And so those are from different flights, which were in different months. So you're looking at different columns of dust.
Okay. That was next part of the question was timing of the flights, different seasons.
Yes, they were. It wasn't optimally different, but let me see. I put those months on one of the earlier slides here. And yeah, so it was July, March, and June. So they're not, this doesn't include like a winter flight, but you know, you've got a quarter of a year at least.
Yeah. And all the fields that you're observing, they're all in the northern ecliptic hemisphere, aren't they?
These ones we didn't go south of the ecliptic. And I think it's really just because we're launching from latitude 33 and we don't want to tip over. We want them to be really close to overhead so we don't get Earthshine in. So,
Yeah.
we need a fly from the south. We need a fly from Kwajalein or something, which is equatorial or Australia to do that.
Yeah, it just makes me wonder a little bit if maybe, given the limited range of seasons and the fact that all these are in the north, that maybe there's some north-south asymmetry them in the cloud and in the models that is causing this difference between the right and Kelsall. And if you had southern fields at similar times, maybe you might not see the same differences for those southern fields.
Yeah, I can only speculate. I don't think, the instrument, I should also say, is now at the bottom of the Atlantic Ocean,
Right.
Which was deliberate, but yeah, so we're not getting any more measurements with this one.
Yeah, my point of view on this is sort of spoiled by working on the Derby data, where we had a huge range of elongations and covered the full sky. So we had a very wide data set available for that. Okay, thanks.
All right, the last question's in the chat from Neil Turner. Is there any evidence for a color difference between the zodiacal light spatially varying and isotropic components?
So I don't think that we would have the power to do that. I think that just with so many fields, the LRS, which is where we got spectral template from, we basically isolate these by taking field differences to isolate the various components. And so with only 5 or 6 fields, we basically made one template. We would need a lot more to kind of look for that. You would imagine a spatial difference, in spectrum if it's cometary origin and, asteroidal origin. I just don't think we have the constraining power to do that, but it's a good point. And, this is the sort of stuff. I will also put a plug. So SphereX is going to survey everything kind of in a Derby orbit and similar elongations, and we're going to have spectra of the whole sky. A resolution at 700 nanometers is only R of 40, which means that we can't fully detect individually this line, but the calcium triplet will be significant kind of at the percent level. So it's going to come down to a spectral calibration thing if we can get our channel to channel gain down. But for large, broad variations in the spectrum, we're going to have spectroscopy on every point in the sky, throughout the year. So I think that we will certainly be able to see, at least at the kind of continuum level, the difference in the Zodi spectral template as a function of position on the sky.
Okay, we're at time. So thank you very much, Phil, and thank you all for coming. Couple really quick announcements. This webinar series is going to take a little bit of a hiatus for the summer, but expect us to come back in September. If you have any topics you want to hear about or talk about, please feel free to contact us and let us know. We are always looking for speakers with cool new results. Likewise, we're putting out an IRSIG newsletter shortly, so if you have a quick one-pager about some cool result you'd like to spread the word about, please let us know. We would be happy to include it. I think with that, we'll stop. Thank you for coming, and thank you for your attention.